Okay, so in this lovely video, we're going to go over some other types of concentrations that you will need to calculate in chemistry. The most common one is molarity. We've already covered that. We're not going to go over it again. We're going to cover 4 more really popular ones. So we have mole fraction, mass percent, parts per million, and molality. Very fun. One example of each, and that's it. Okay? Here we go with concentrations. And the most popular one that we will use in chem is molarity. Okay, if you need more help on molarity, which is just moles of solute divided by liters of solution, there's a molarity video, or ask whichever teacher you have because they're awesome. Okay, good. So we're not going to go over molarity. Instead, we're going to go over the other main 4, which is mole fraction, mass percent, parts per million, and molality. So here we go. All right, we're going to start with mole fraction. Okay, mole fraction is really easy. Okay, it's a fraction of the amount of moles of one substance in your solution divided by the total moles of your full solution. Okay, and the most common way that this guy is used is when we talk about gases. Okay, so if you had like a gas chamber, or you have a mixture of gases, mole fraction is actually really useful in chem because it helps us identify the partial pressures of each gas. We can use mole fraction to do some cool things with gases, okay? We'll look at this in just a second. So the little, make sure you're aware of with mole fraction, first thing that's really important is that there are no units. Okay, so for once ever, you don't actually put units after your answer if you're asked to solve for mole fraction, because it's moles divided by moles. So there's no units, okay? And the other thing that you're going to have for mole fraction is it's always going to be a decimal between 0 and 1. Okay, so for example, you're going to get 0.24. or something, okay? It's going to be a decimal between 0 and 1. And actually a good way to double check if you solved the problem correctly, you should be able to add up all of your mole fractions. And if you add them all up of every substance in your solution, you should get exactly 1.0, right? You have one whole solution. Okay, so the example question for this dude, all right? Find the mole fraction of carbon dioxide in a solution with 4.82 grams of carbon dioxide, 5.8 grams of oxygen, and 9.2 grams of nitrogen, which would be exactly this in a gas chamber, right? So if you had your N2s, which are like the pink guys, mixed in with some oxygens, which are the blue guys, some O2s, mixed in with your carbon dioxides. So that would be 1 carbon and 2 oxygens. Okay, and I'm just trying to figure out what is the fraction, what's the mole fraction of my carbon dioxides within that thing, okay? Easy, all right? Unfortunately, okay, almost always if you're gonna be asked to solve for mole fraction, they're not just gonna give it to you in moles. They're gonna make you do molar conversions first. So you look at your handy dandy periodic table, and we're going to have to convert some molar masses, okay, to actually solve for moles. So I have carbon, which is 12.01 grams per mole. I have oxygen, which is 16. And I have nitrogen, which is 14.01. Okay, and I can just use those 3 for calculating all this. So I need to convert, okay? Womp womp. So if I start with 4.82 grams of carbon dioxide, I need to get out of grams and get into moles. So we're doing a mole fraction here, okay? So if I have 1 carbon, 12.01, plus 2 oxygens, 16 and 16 is 32, I should get 44.01 grams for every 1 mole of carbon dioxide. If you're not 100% sure on how to calculate your molar masses, please, dear God, review, ask, go to office hours, do something. I'd be happy to help in any way I can with molar masses, but we should be good with that by now, okay? So your grams and grams will cancel, and you will get some amount, 0.11 moles of CO2, okay? You have to do the same thing. Convert for 5.8 grams of oxygen. Okay, I want to get out of grams, so grams of O2 on the bottom, on your denominator. Moles of O2 up top. 1 mole of O2, 2 oxygens, it's going to be 32 grams. Do a little division. Grams and grams will cancel. And you get 0.18 moles. Last conversion is 9.2 grams of nitrogen. It's 28.02 grams for 1 mole. All right, 14.01 twice. Again, grams and grams will cancel, and I will get 0.33 moles of N2. Okay. Now I add this up, right? I need my total moles. So 0.11 plus 0.18 plus 0.33 gives me 0.62 total moles. And now I have everything I need to actually solve for my mole fraction, okay? So I'm worried that's gonna run out of space. I'm just gonna scoot that up. All right, so my mole fraction is the moles of the one substance I want, which in this case was CO2. So 0.11 moles of carbon dioxide divided by my total moles, 6.2, and it equals 0.177. And there's no unit. Mole and mole cancel, no unit. So my mole fraction of carbon dioxide for this question is 0.177, 177 thousandths. Easy. All right, next. Okay, I'm not going to spend a million years on this. All right, mass percent. Okay, mass percent is a really easy concept. Okay, it's a percentage, so you're going to end up multiplying by 100, and it's mass. So I need the mass of my solute divided by my total mass, okay? And again, multiply by 100 because it's a percent. So the question would be, find your mass percent of a solution of 0.5 moles calcium chloride in 1,700 milliliters of water. Okay, so right off the bat, hopefully we notice moles is not in a mass, it's not in grams, and milliliters is not in a mass, it's not in grams. So we have to do a little bit of converting. And also, it's giving you the name of the compound, the name of the ionic compound. So please make sure that you know how to go from a name of an ionic compound to the actual chemical formula, okay? So calcium has a 2+ charge. Chloride has a 1- charge. When these guys come together to actually make calcium chloride, they need to be electrically neutral. So 2 chlorides for 1 calcium, CaCl2. That'll be important because we'll need to convert. Okay. Again, we're going to have to use our periodic table to convert from moles into mass now because I want a mass percent. So if I start with 0.5 moles of CaCl2, I now want to convert to grams, which means I need to look up on my periodic table and find my molar masses. So I guess I'll write it over here. Not in the same color. All right, calcium. It's like 40.08. Chlorine is 35.45. There's 2 chlorines, right? So times 2 is 70.9. So you're going to add up your 40.08 of the 1 calcium, 70.9 of the 2 chlorines, and you get 110.98 grams per mole for CaCl2. All right, so 1 mole of CaCl2 is 110.98 grams. Moles and moles will cancel, and I will get 0.5 times 110, so half of that, which is 55.49 grams. Okay, so that's the mass of my solute. Now I need to figure out how many grams is 1,700 milliliters of water. Okay, this is not tricky. It's on the back of your periodic table. Also, if you remember density at all, right, the density of water is 1 gram per milliliter. So if I have 1,700 milliliters, that means I have 1,700 grams of water. Yay! So I have my grams of water, I have my grams of my solute, and now I can plug in. And here's where people make mistakes. Okay, so mass of my solute, that's easy, 55.49 grams CaCl2. What most people will do here is they will just put 1,700 grams of water, and then they will times by 100 and call it good. This is not my total mass. 1,700 is not my total mass, right? Total mass is my water and my calcium chloride that I'm adding to the water. So make sure you add your 55.49 grams of CaCl2, okay? I have to have the total mass. And this is easy. This is just 1755.49. All right. So I actually have 55.49 divided by 1755.49 grams times 100. Okay. Grams and grams would cancel. And I get a lovely answer of 3.16%. Okay, so of this calcium chloride solution, 3.16% of it by mass is calcium chloride. The rest of the percentage, so 96.8-ish % of the mass is just water. Easy enough. All right. Next is parts per million. Okay, and parts per million actually becomes really important when you are talking about the Environmental Protection Agency, the EPA, because we talk about parts per million or even parts per billion when we're talking about safe drinking water. Okay, in the 1970s, I think, look it up, like 1975, 1974, they passed what's called the Clean Drinking Water Act, something like that, and what it did was it gave maximum contaminant levels of different things that were poisonous in our water. And we have to, regulate to make sure that we're not poisoning ourselves and killing ourselves, okay? So you can go on the EPA's website, you can look up different metal contaminants, different inorganic, organic contaminants, whatever, and it will give their maximum contaminant level, MCL, maximum contaminant level. Milligrams per liter is the same as parts per million, okay? And this is really good, again, because we want to make sure that we're not going to drink water and die, okay? Or drink water and poison ourselves, which is why it's so important to actually monitor this stuff. You should look up Flint, Michigan, if you don't know about it already. They were far beyond the maximum contaminant level. Okay, so if, I actually have this, okay? All right, parts per million is almost the exact same as mass percent, except It's per million. So instead of multiplying by 100, I just multiply by a million. That's really easy, okay? So you still just take the mass of your solute, divide it by your total mass, multiply by a million. Easy, okay? So if you were given a question like you found 0.02 grams of nitrate in 12 kilograms of drinking water, you could be asked to find the parts per million, and you could be asked to determine if the water is safe to drink. Okay, so I already highlighted it for you just to make it easy. All right, if I have 0.02 grams of nitrate, and I'm trying to figure out if that amount of drinking water is safe, or that amount of nitrate in 12 kilograms of drinking water is safe, I look up my maximum contaminant level from EPA, I find nitrate, and I find that my max level, MCL, maximum contaminant level, is 10 parts per million. So when I do my calculations, I better not exceed 10 parts per million, otherwise I'm poisoning myself, okay? Here we go. So I have mass of solute divided by total mass. It needs to be in the same units. Right now I have kilograms and grams. Okay, if you don't remember how to do your metric conversions, please review. But if I have 12 kilograms, all I do is multiply by 1,000, and that's 12,000 grams of water. All right, so now I can just plug and chug. Basically, this is easy. All right, so I have 0.02 grams of nitrate in my total mass, 12,000 grams of water. And again, that's not my total mass, right? I have my water and my solute that's dissolved, and 0.02 grams of nitrate. Now, technically, the 0.02 grams is not going to change your answer at all, but if I were grading your test and you didn't show me that you understood the concept of total mass, I would absolutely mark you off, okay? So make sure you're showing that you understand this is the total mass, right? 12,000.02 grams. All right, so you basically get 0.02 divided by 12,000.02, and it's parts per million, so times a million. And you get a lovely answer of 1.67 ppm. Okay, so that's the answer to your first question. Find parts per million. Check. 1.67. Is this water safe to drink? Yes, this is safe. It is below the maximum contaminant level of 10. So you're good to go, okay? You're not going to die if you drink this water, right? Good. Last one, all right, is molality, okay? Molality. So molality actually becomes really important when we're dealing with freezing point depression and when we're dealing with boiling point elevation, which we also use in this unit. Okay, so you are going to need to know how to calculate molality. And the kind of symbol for molality is the lowercase italicized m. Okay, all right, this is relatively easy. It's moles of your solute divided by kilograms of your solvent. Okay, so a quick example. Saline solution for contacts is made in big batches, okay? They do not just like, I had a picture of it, like you need to see it, okay? But saline solution for your eyes, when they're making this in the actual factory that they make it in or the lab they make it in, they don't just make it in 4-ounce bottles at a time. That would be ridiculous and wasteful, right? So they make it in big batches, and then they separate them out and fill the bottles, and then we buy them and we put our contacts in our eyes, okay? So the actual way that they make this is they make it a liter at a time, okay? So they make it with exactly 175.5 grams of NaCl, it's just salt, saline solution, in every 1.5 liters of water. I think I said 1 liter at a time. It's a liter and a half at a time, okay? So 175 grams of your NaCl in every 1.5 liters of water, okay? Of course, because I'm cruel, we're gonna have to calculate and convert from grams to moles. So sodium is 22.99 grams. Chlorine is 35.45 grams per mole. Add those dudes up, you get like 58 point something, 44? Yeah. For NaCl. All right, and now we calculate. So I start with 175.5 grams. I need to get out of grams, get into moles. And my molar mass is 58.44. Terrible handwriting. Hopefully you can read that. Okay, grams and grams will cancel. And I'll get a lovely answer of 3.166 moles. And I'm in 1.5 liters. I can convert liters to milliliters, so that's 1,500 milliliters. I don't want to actually do that though. Oh my God. Okay, because I want kilograms, okay? You could do that. This is, if you wanted to go the long way, you could. This is not wrong. You could go milliliters, and then the density of water is 1 gram per mil, which would mean this is 1,500 grams. And then you can convert back to kilograms, which would be 1.5 kilograms. Or you could just recognize that liter to kilogram would be a 1-to-1 ratio for water instead of going through all these steps. But hey, if you need to, you can do it that way. All right, lovely. Clearly this is the last problem. I'm losing my mind, okay? So I have kilograms, I have moles, I can calculate. 3.166 moles divided by 1.5 kilograms. And I would get 2.11 italicized M NaCl. And the way I would say this, I call this a molal solution. Okay, so I'd say 2.11 molal sodium chloride. Okay, just like for molarity, I would say, you know, it's a 4 molar solution. This is a 2 molal solution. Fun times, okay? So that's it. Those are the other types of concentrations you'll need to calculate. This is the longest video ever, so hopefully you get it. Good luck.